Okay, so question over here says electric field due to an electric dipole on its axial plane is given by, so correct answer will be option B, that's we have already derived 1 by 4 pi epsilon naught. It should be epsilon naught, okay? 2 pi r upon r square minus a square whole square, okay? Without epsilon naught, like epsilon, there's a misprint here, it should be epsilon naught all over, okay? So 2 pi r upon 4 pi epsilon naught r square minus a square. Let me move to the next question. This question over here says electric field due to an electric dipole on its equatorial plane. Equatorial plane, we know it's minus p upon 4 pi epsilon naught. Again here it should be epsilon naught, epsilon naught, epsilon naught, and r square plus a square whole raised to 3 by 2. So it should be option C. Let's see the next one. An electric dipole consists of two opposite charges of magnitude this much. So let me just write here Q will be equals to 4 into 10 to the power minus 5 Coulomb and separated by a distance of 2 meters. So 2A itself is 2 meters. The dipole is placed in an external electric field. So electric field here E will be equals to 4 into 10 to the power 5 Newton per Coulomb. What will be the maximum torque? Now we know that torque tau is equals to PE sin theta. But for maximum torque, theta is 90 degree, right? So torque tau will be equals to PE. And dipole moment is nothing but 2AQ into E. And 2A we already have here 2 meters, Q as 4 into 10 to the power minus 5, and electric field is 4 into 10 to the power plus 5. 4 4s are 16 2s are 32 Newton meter. That will be our correct answer. So option A, that's our correct answer. Let's see the next one. Over here says the torque experienced by the electric dipole having dipole vector given by, so dipole vector is given by P, and that is equals to how much? 2I minus 3J plus 4K, right? And placed in an electric field E, that is given by minus 3I plus 4J minus 2K. So torque tau, we know that it is equals to P cross E, cross product with E. So how do we find cross product? Let me just write here I, J, K, and let's write first the components of P, that will be 2 minus 3 4 minus 3 4 minus 2. So that will be torque tau equals to, let me just multiply using cross product. So when you are multiplying using cross product, right here I cap, ignore the row and the column of this, okay? So we left with 4 elements, and that is, yes, 6 minus 16 minus j cap into how much it will be? Minus 4 and plus 12 plus k cap into 8 minus 9. So that will be minus 10 I cap minus 8 j cap and minus k cap. That will be our torque. And what's the unit? Newton meter. Option A. Let's see. So question over here says the torque experienced by the electric dipole having a dipole vector given by P, which is equals to I cap minus 2j cap plus 3k cap, that's dipole vector, and placed in an electric field E, that is equals to minus 2I plus 5j cap and plus 3k cap. So torque tau will be equals to P cross E. So let's find the cross product. I cap, j cap, k cap, and P here is 1 minus 2 3, E here is minus 2 5 and 3. So this will be I cap into, torque here is I cap into 3 2s are minus 6 and minus 15 minus j cap into 3 and plus 6 plus k cap into 5 and minus how much? 4. So this will be minus 21 I cap minus 9 j cap and plus k cap. That's option C. Understood? Let's move to the next one. The torque experienced by an electric dipole will be maximum if the angle between the electric dipole moment and electric field is maximum, it's 90 degree. We have discussed in the theory part. Let's see the next one. So question over here says an electric dipole consists of two opposite charges of magnitude. So let me just write here Q, that will be equals to 3 into 10 to the power minus 5 Coulomb, separated by a distance. So 2a itself is 1 meter. The dipole is placed in a uniform external field of electric field E, that will be 4 into 10 to the power 8 Newton per Coulomb. The maximum torque experienced by the dipole. So torque tau, that will be equals to, for maximum theta is 90 degree, we know, so it will be PE. P here is 2aq, so 2aqe, and 2a is nothing but 1, q is nothing but 3 into 10 to the power minus 5. Electric field E value is 4 into 10 to the power 8. So it will be how much? 4 3s are 12 and 10 minus 8 minus 5, that's 3. So it's minus 3 here given, so correct option should be option D, none. Yes. So let's see the next one. What charge would be required to electrify a sphere of radius 25 centimeters? So let's imagine a sphere and the radius of the sphere is 25 centimeter over here. So as to get a surface charge density, so R, let me write here 25 into 10 to the power minus 2, that is our radius of the sphere. And so as to get a surface charge density, we know that it is denoted by sigma, that is nothing but 3 by pi Coulomb per meter square, that's a unit, standard unit of sigma. Now sigma is nothing but charge upon area, we know that from the previous lecture. So area here is nothing but 4 pi r square, that is the outer surface area of this sphere. So charge we are looking for, so Q will be equals to sigma into 4 pi r square. Let's put the values. Sigma over here is 3 by pi into 4 pi into r square, which is 25 into 10 to the power minus 2 whole square, which I can write it as 25 into 25 into 10 raised to minus 2. Now we can cancel pi with pi straight away, and here we left with 4 into 25, that's 100, right? So 4 into 25 is 100 and 100 into 10 to the power minus 2, all these gets cancelled. We left with 3 into 25, which is 75 into 10 raised to minus 2, and that is nothing but 0.75 Coulomb. That's our correct answer. Let's see the next one. Let's start with this problem. The question says over here, a charged spherical conductor has a surface charge density. Let me write here as sigma, that is equals to 0.7 Coulomb per meter square. When its charge is increased by, now be very careful because the word by is very important here. Sometimes they can write it as when its charge is increased to. So it will have a different meaning. If it is saying increased by, which means the new charge value will be higher than the previous one, right? Yeah. So it is saying when it is increased, let's say the previously charge was Q. Now the charge is Q dash, and that will be equals to Q plus 0.44 Coulomb. Okay. This is called increased by. Sir, what if it was increased to? Then you will not write Q plus this thing. You will straight away write 0.44. Okay. The charge density changes by, again the word is changes by. Changes by means again the sigma dash will be equal to sigma plus 0.14, and sigma is nothing but 0.7. So let me add straight away 0.14 and it will make it 0.84. That will be its new surface charge density. Find the radius of the sphere and the initial charge. So let's assume that sphere is having radius r, that will remain same in the previous case as well as this case, right? Because only the charges and sigma is changing. So in the previous case, sigma will be equals to Q upon 4 pi r square. That will be our first equation. Now when the charge is increased, it will be sigma dash, that will be equal to Q dash upon 4 pi r square. Still it is the same, r is same. Now let's divide sigma 1 and sigma 2, or equation 1 and equation 2. It will be sigma over sigma dash, that will be equal to Q upon Q dash. I hope this is clear. Now this implies sigma, that is 0.7, sigma dash, that is 0.84, Q is Q, and Q dash is Q plus 0.44. Correct? Now we can do one thing, we can cross multiply, and before we do that, let me just simplify here. Let me remove this point, the decimal, and this will give us 70 over 84, that will be equals to Q over Q plus 0.44. Let's cross multiply. So let me do it over here. It will be 70Q plus, let me multiply 70 with 0.44 and that will give us 30.8. That will be equals to 84Q. Any doubt? So 30.8 will be equals to 84 minus 70. That will be how much? It will be 14Q. So Q will be equals to nothing but 30.8 divided by 14, and that's our 2.2 Coulomb. That's our charge on the sphere. Initial charge on the sphere is 2.2 Coulomb. Now if this is the charge, let's put it in back in equation 1. So from equation 1, R square is nothing but Q over 4 pi sigma, right? And that will be Q is how much? 2.2 over 4 into pi. Let's put it 3.14, and sigma is 0.7. This is R square, right? So let's simplify it. 4 into 3.14 into 0, or let's make it as 22 by 7. That would be better option. Yeah, so that will be 22 by 7. And let's remove this point and it will become here into 10. Let's remove this and you will get here 10. 10 and 10 gets cancelled, 7 and 7 gets cancelled, and this will get. So R will be 1 by 2, because 1 by 4 root is 1 by 2, that's 0.5 meter. That's our radius of the sphere and that's our charge, 2.2. Any doubt? Let's see the next one. Okay, so question over here says 64 drops of radius 0.02 meter and each carrying of 5 microcoulomb are combined to form a bigger drop. Find how the surface density of electrification will change if no charge is lost. Okay, so first of all, let's find what will be the relation between the radii of the bigger one and the smaller one. So if let's imagine that such small 64 drops are combined together to form such a big drop, then volume of the smaller drop will be 4 by 3 pi r cube, right? If I multiply it with 64, this must give us the volume of the bigger drop, 4 by 3 pi capital R cube. Let's cancel out pi and pi both the sides. So r cube will be equals to 64, r cube into 64, that will be equal to capital R cube. And that will be 4r, that will be equals to capital R. That's our equation number 1. That gives us relation between the radii of the smaller drop and the radii of the capital drop, right? Now, if this is the situation, let's see what is the sigma. Sigma for the smaller drop, let me call it as sigma. That will be equals to the total charge Q upon 4 pi small r square. That's our first one. And sigma dash, that will be our total charge on this larger drop. That will be Q dash. It won't be Q because there are 64 such Qs upon 4 pi capital R square. That is equation 2. Now let's divide sigma and sigma dash, that is equation 1 and equation 2. So sigma over sigma dash, that will be equals to capital R square over small r square, and Q over Q dash. I hope this is clear, right? Now capital R is nothing but small 4r. So let's substitute the value sigma over sigma dash, that will be 4 4s are 16 r square whole divided by r square into the total Q. Q is given as 5 into 10 to the power minus 6. That's the charge on a single drop, but there are 64 such drops. So Q dash will be 64 into 5 into 10 raised to minus 6. Let's cancel out r square with r square. 10 to the power minus 6, 10 to the power minus 6, 5 and 5. 16 4s are 64. So sigma upon sigma dash is 1 by 4. That's the ratio in which the charge densities will alter. Let's see the next one. So in the last lecture we discussed about continuous charge distribution. Let's move to another topic, a small topic we will discuss, and the role of this topic will be very crucial in our next part, which is the last part of this chapter. So let me write here, this is known as electric flux. Now 90% times the students, they understand this electric flux wrong in school. Why they understand it wrong, we will see that within a minute. So let me just write the definition of electric flux. So electric flux is nothing but, you can define it as, it can be defined as the bunch of electric field lines passing through a given area. So pay attention now. If there are field lines which are going or passing through any charge, let's take a random example. I'm just taking as plus q, you can take it minus q also, doesn't make any difference. So let's say these are field lines. I'm just randomly making some field lines here, so that they don't touch each other, but these are the field lines which are coming out of this charge and they are going away from the charge. So let me just draw a few so that you get a slight idea of what is flux. So these are field lines which are coming out of this particular plus q charge. Okay. Let me just draw it like this. Let's make it like this. Okay. So they are emerging out from the charge only, but okay. So let's assume these are our field lines which are going radially outward due to the positive charge. You can see here that the field lines are very dense around the charge, right? And if they are very dense around the charge, which means the field is stronger in this region compared to the field which is in this region. So as this is obvious because we know the value from mathematical relation, E is equals to kq by r square. As the r, the separation increases as we go away from the charge, the electric field decreases, right? Now here if you take a small area, now be very careful, I am not dealing it in 2 dimensions, I am dealing it in 3D. Okay, so don't just take it like as you can see it on the board in the classroom or the screen here. Okay, it's a 2D, but in reality the field lines are going in 3D, in all possible 3 dimensions. If I imagine a small area like this, okay, so just to make it more specific, let me just draw it like this. Okay, this is our area, and if I make the similar kind of area in this region, and ideally you can see that they look quite, just assuming that they both are equal in size, right? Yeah. So if you look at the area A and if you look at the area B, let's count the field lines passing through A. 1, 2, 3, 4, 5. Okay, 5 field lines are passing through A. Number of field lines passing through B, though they are both are equal in area. Okay, so the field lines passing through B is only 2. So the field lines passing through a given area will determine the intensity of the field. That will decide that how much stronger the electric field will be, right? So these bunch of field lines passing through a given area will be defined as flux. Very crucial, important point. Okay, if you know the flux, you know the field. If you know the field, you can find the force, right? So this is very important part. So flux is bunch of field lines passing through a given area. Yeah. B, exactly. So flux at A will be higher than flux at B, and mathematically it is given by a symbol like this. It is phi. Why we are using phi? No sense of this question. It's just a symbol, right? So flux phi is nothing but electric field E dot area. Area, be very careful here with the area, E dot A, and when you remove this you get n cap. N cap is normal to the vector. What is the use of this? I will explain. Okay, and when you remove this dot product you simply get EA cos theta. That's our electric field. Okay, and when you are using integration we will make use of E dot ds integration. That will be our phi. Okay, so these are the 3 common used relation in case of flux. Okay, now what is the role of n cap? What is the role of cos theta? We will see within a minute. Okay. Okay, let's see what is the role of cos theta and n. Now try to understand it very carefully because they will use these concepts, and this will be repeated again in chapter 5 or 6. Okay, so see what is happening. Let's imagine a Captain America shield. Okay, you have seen Captain America shield? Yeah. Okay, now because it's a 3D, so you have to be very careful about that thing. Okay, now somebody is firing bullets, right, in this direction. Okay, obviously you will keep the Captain America shield like this, so that all bullets will go and stuck on the shield and you will be safe here. Now what happens if somebody is firing the bullets from this direction? So that is obvious that you will be killed, right, if you are keeping the shield in this same position. Sir, what happens if they are firing from the top? You have to keep the shield like this, right? So be very careful, understand the core concept. What is happening here is, what is the direction of electric field? So direction of electric field is this side. What is the direction, how the area is placed? So the area is placed like this. Where will be the normal to this area? So normal to the area will be, you can point it in this direction or you can point it in this direction. These both are normal. We call it as perpendicular to this area, right? So if I am assuming if the normal is in this direction, ideally speaking, if this is the normal and the direction of electric field is also in this direction, what is the angle between the normal to the area and the electric field? Theta is 0 degree. 0 degree. Be very careful. I am repeating again. Be very careful. Okay. There are two words. I will write it in statement. Put it in your notebook. Okay. One is normal to the area. Normal to the area. Another word is area. Okay. So normal to the area and electric field, theta is 0 degree. But angle between, this is, okay, so I am writing in this case, or you can draw this diagram also in your notebook so that later reference, or anyways, I'll post this on the YouTube, okay, so you can watch it again. Very crucial part. So theta is 0 degree in case if you are finding the angle between normal to the area and electric field. Okay, and electric field vector. Theta is 90 degree in this case between area and electric field vector. Sir, how? See here, I am drawing a diagram. Again, electric field is this and it is making 90 degree with the exactly area of the shield. It is making 90 degree, but the angle between the normal to the area and electric field, they are parallel. Look at these two black lines. Now what if somebody is firing bullets from the top? Now from the top, look at this. If this is the field direction going downward and you are still keeping the shield like this, the angle between the field and the shield is 0 degree in this case. But normal, sir, normal will still remain here only. So look at this angle. Now in the second case it is 90 degree. Clear it is? Second case you didn't understand. So let's do one thing. Let's reshare the screen. Okay. Next, can you see it? There is a shield like this. Okay. I want to explain you from 3D. Look at this 3D. Can you see the 3 dimension? All around, right? Okay. Now pay attention now. Let's recall our concept. Okay. So if, one second, let me just add here pen. Yeah. Let's say somebody is firing bullets from this side. I'll show you the whole view. Now if somebody is firing bullet from this side, look at the front view. Can you see it? Okay. Coming back to this situation. Can you see the field lines? The field lines are going like that. Now if I extend this field line, okay, if I extend this field line will go from here and make what angle with the area? Tell me. Exactly. Now if I want to make a perpendicular to the area, look at this perpendicular to the area. Is it the perpendicular to the area? Yes. Sir, make a 90 degree here. This is 90 degree, right? Now what's the angle between electric field and perpendicular to the area? 0. Both are pointing in the same direction. Look at this. Yeah, 0 degree, right? And when it is 0 degree, between what? Between the normal and cap and electric field, the angle is how much? 0 degree. And in this case, maximum flux will pass through this shield, right? Theta here is 0 degree. So cos 0 is 1, right? So flux phi is E dot A. Now what happens if somebody is firing bullet like this, instead of firing like this, if somebody is firing bullet like this? Sir, in this case, you should keep the sheet like this, right? Yeah, you should keep it like this. But let's suppose if you are not keeping it like this. So let me just remove this part. You should keep like this shield to save yourself, right? Okay. 1 second. It's okay. You should keep the shield like this, right? But you are not keeping like that. You just keep the shield like this. Now what happens? Let's see this. Let's see the top view. Now bullets are coming like this. And still the shield is like that. This is our electric field vector from the top. It is going like that, right? What's the angle between? Straight down, right? If it is going straight down. And what? Oh yeah, exactly. So electric field and the area is 0 degree here. Between electric field and the area, because you can't see the shield. It's parallel. It's completely parallel. Okay. But look at the normal. Normal is this one. Yeah. So between the normal and the electric field, what's the angle? Yeah, 90 it is. Let me just see it again in the same way. So theta is what? 9. Between the normal and the electric field, the angle is 90 degree. And if it is 90 degree, then the flux is 0 in this case, which will pass through the area. So in the first situation, the flux will be maximum. The flux will be maximum in this case, first case, but in the second case, the flux will be 0. Why 0? Let me repeat again. Angle you always take. Angle is measured between whom? Normal to the area and electric field. Always never look at the angle between electric field and area. Always look at the angle between normal to the area and electric field. Okay, sir. Do one thing. Just make a switch. Let's say this is our notebook, and let's remake it as 0 degree. Just 0 like this. 0 degree I made it. Okay. Do you still have your normal at the same place? Now where will be the normal? It will be going vertically upward in this case. This is the new normal. So let me write it as N2. Because these will be the normals perpendicular to the surface, right? And where is the electric field this time? So still electric field is like this. What is the angle between? Yeah, what's the angle between electric field and normal this time? So 90 degree. And if it is 90, cos 90 is 0. So now the flux will not pass through the area. You can see that it's not passing and hitting the area. Yeah. Okay. So previous case. Yeah. Yeah. Electric field lines are case 1 only I am taking. Case 1 only I am taking. 90 degree. Yeah. Perpendicular to the normal. That's why the flux will be not passing through the area. You can see that. Okay. 0. Yeah. So electric field and area becomes parallel to each other. Flux becomes 0. If I slightly change the angle, look at this. I am changing the angle. As the angle is changing, the shield will stop more and more bullets. And if the shield is at perfectly 0 degree, no bullets are stopped, right? If I am standing over here, I will be killed in this situation, right? But if I am keeping the shield, if I slowly increase, the more and more bullets will stop. Now, when you are saying the bullets are stopping here in this case, you simply mean that flux are passing through the area. Understood the concept? This is very important for this chapter as well as because this is, I have found 99% students, they understand it wrong and they get confused with the angle. So just the statement which I have written, though I don't know at what angle, yeah, here angle, this is so perfect. The angle is always measured between the normal to the area and electric field. Yeah, now it makes more sense of how the theta is. So all this is very crucial. Try to write it. This is very important part. Theta is normal. Angle between normal to the area and electric field is always considered when you are finding the flux. And we have 3 formulas for flux. We will do tomorrow problems on this. And E dot ds integration, E dot a dot product, and directly if the theta is given. So this is obvious that you will find a function in any problem. You use this one, integral. When you find 2 vectors, you use this straight away. And when you find an angle, you use the third one, right? But angle is always measured between normal to the area and electric field. And to confuse you, they will give you the angle between area and electric field.